very lax definition of the scope of the workshop, so that I could be invited to come. Always a pleasure being here. Okay, so I will talk a little bit about a problem I've been wondering about for 10 years now. Involves, as the title says, black hole perturbation theory and some uses for conformal blocks, which I think harken back to the old works of Zamolodchikov and Teschner, Dorn, Otto, these people. Okay, so this is a joint work between myself, João Paulo, who is a former student, now is in a postdoc of Maurício, who works at São Paulo. It's been a couple of papers. This is something technical about expansions of conformal blocks. It's in JHAP. This one is in PRL, and this one is an accompanying BRD that came out last year. All right, so okay, so I guess that most people here know, but I'm just trying to get everybody on the same page. This it's basically how to understand the internal structure of a black hole. And as usual, physicists, we like to throw things at the wall and see what breaks. So the first tool to try to understand the internal structure of black holes is actually to hit it down with a hammer and see what comes out of it. In this case, there are some oscillations that are produced in space-time. These oscillations have some frequencies that are quasi-normal modes because they have inherent imaginary part. So that means that they not only they propagate, they oscillate, they also decay. The decay is actually important for many applications of this because you have relaxation times for the SCFT. You have the ring down phase of black hole merger events and all the applications, especially in holography. Of course, I guess that even the most cynical person that would look at this problem said that the most interesting, at least the most physically relevant one, is the actual four-dimensional Kerr black hole, because these are the ones that people take photographs of. So there's some actual chance of trying to combine or trying to confront whatever compute here with the experiments with nature. And if you bottom down to this, in the linear regime, this problem is actually quite simple. You work with the linearized Einstein's equations, and what you have at the end of the day is some propagation of some spin S field in some background. So you just write down something like the wave equation. In this case, black holes that I'm considering, I mean, and this is the Kerr black hole, by the way. I didn't write the metric down, but it is the Kerr black hole. The Kerr black hole has two Killing vector fields. You can do separation of variables because of the Killing-Yano tensor structure. So you can write an ansatz for the solution like this. I'm going to do scalar fields here, although they are not very realistic, because by the end of the talk, I think that you're going to see that there are some effects coming from the mass that are the ones that I'm trying to focus on. Anyway, continuing. If you just plug this back in the equation, this is a very simple problem. I said it's classical problem, really. You have some ordinary differential equations for the angular part of the wave function and some radial equations, which are known usually as the Tolkowski equation, although these ones, they have mass, so they have some extra parameters here. These equations, they have some interesting mathematical history. It's more than 100 years. They're called the confluent Hoyne equations, and generically they have this form. It varies a little bit, but this is the one I like to look at. And if you remember the theory of your theory of Fuchsian differential equations when you're studying mathematical physics, this equation it's characterized by the fact that you have two regular singularities. In this case, that's z equals 0 and z equals t. These are z is related to the actual geometrical coordinate that I defined last slide. I'm going to talk about that a bit more soon. and another irregular singularity at infinity that's characterized by this constant term here and this 1 over z fall off at infinity. And this is actually quite physical if you go past the mathematical blurry. This means that the wave function near the singular points, they have some polynomial behavior. And this means that if you write this in terms of the tortoise coordinates, for instance, this will have some purely ingoing and purely outgoing waves at the horizons. And you have some exponential behavior at infinity, which just in this case means that the space is asymptotically flat, and the solution of the wave equation becomes spherical waves, regular spherical waves with a definite frequency at infinity. So the analytic structure of the solutions here is quite involved. You have some branch cuts at each of the points because of these coefficients, which in general are complex numbers. And you also have Stokes sectors here at infinity, which is quite odd and something that usually takes a lot of time to explain to physically minded referees. But hopefully you get there. Okay, so why does that happen? Help me. I can go back and look at the generic form of the Hoyne equation, or the confluent Hoyne equation in this case, and try to compare with the equations that I found for my angular part of the wave function and the radial part of the wave function. So if I just do the change of variables here, I find that the singular points of the angular equation are related to the south and north poles of the sphere, which in this case is parameterized by u and phi, u being cosine of theta. And what I want, it's the usual stuff when I try to define Legendre polynomials in mathematical physics. I want regular solutions that are regular both at the north pole and the south pole. The radial equation is another thing. You have, it's quite interesting actually, because you have singular points of the wave equation at the Killing horizons. So you have a singular point associated to the outer horizon of the curved black hole, another singular point at the inner horizon of the curved black hole, and something that I call a Killing horizon by abuse of language, but it's really at infinity. That's the irregular singular point. And like I told you, usually you have spherical waves here, and here you have incoming and outgoing waves when you write it down in the tortoise coordinates. Strange fact that will become relevant later on is that the separation of variables does not commute with parity transformation or time reversal. When you do time reversal, you send the frequency to minus the complex conjugate of the frequency, and you change the z component of the angular momentum to minus the z component of the angular momentum. The value of m changes. So the usual arguments that I have for stability of the system do not apply here. The system may actually become unstable. It's something that you just have to check by taking this effective potential and see if all the solutions, they have a negative, positive frequency. The funny bit here is that in order to solve for quasi-normal modes, and this is something I'm going to do later on, you have to impose boundary conditions that are non-local. So you have to impose that no energy is leaving the black hole, so the solution is purely ingoing at the outer horizon and spirally outgoing at infinity. This is a sort of a Sturm-Liouville problem, just like the others. So you expect some discrete spectrum of the frequencies, but it's not of the usual type, because here you can, for instance, find a genetic connection formula that allow you to relate solutions at one pole to the other. And here it's not so clear how to do that. Or at least it wasn't so clear until a few years ago. So just to make some deference to some people in the audience, I guess, the method of choice to compute these quasi-normal modes relies on the so-called flow case solutions of the of the Hoyne equation. You plug down an ansatz like this with the whole Laurent expansion, and this is supposed to converge to analytic function. And this, at least this part here, is supposed to converge to analytic function inside an annulus. This means that, for instance, in the radial case, that would converge to analytic function in a region between the outer horizon and infinity. There is a 1 here, but it's just for the sake of clarity. I mean, in practice, this function here would converge to up to infinity. And if you plug this back in the equation, you get a 3-term recurrence relation that you can solve by a continued fraction. There are some other methods based on Hill determinant and so on. You see that I introduced here some parameter sigma, which is not fixed. I want to fix that by solving this equation. And you can think of this complicated equation here as some implicit definition of this parameter sigma. I'm going to go back to this parameter sigma in a moment, but there are other parameters that show up here. This thetas, c and t are parameters that I can read up in the Hoyne differential equation. C being this coefficient here, and thetas being this set of theta 0, theta t, and theta star, and t being, of course, the position of the second parameter. So mathematically, the problem is well posed, but recently there has been some developments in understanding the analytic structure behind this equation. So I'm going to say some words about this. The expansion that you have here, this method of choice, works for, there I go, getting ahead of myself. This expansion here works for small t, so you can plug this ansatz here for relating this c parameter that shows up in the equation, the sigma parameter that I introduced, and then you get some series, which is quasi-analytic. There is a principal part here, and then there is an analytic function. I told you that there is a nice physical interpretation of the singularities, because you have one singularity at the inner horizon, one singularity at the outer horizon, and another singularity at infinity. There is also a nice interpretation of the coefficients of this expansion near this horizon. So just to give remind you of some context, I told you in the last slide here that this parameter theta, this should be theta t here. I forgot. I always forget about this. Okay, here this should be theta t. So thetas, they control how the solution behaves near the singularities here, and the thetas that you read up from the radial equation, they can be cast in this form, where omega here is the angular velocity of the horizon, and T is the temperature of the horizon. And if you remember the first law of black hole thermodynamics, this is exactly the entropy intake of the black hole, the entropy change of the black hole as it absorbs a quantum of energy omega and angular momentum m. I wish I had some interpretation of what happens at infinity, but perhaps you have something like that showing up if you work out the second law with enough detail. These thetas, they diverge at extremal limits. So in general, when omega does not go to some multiple of small omega, does not go to some multiple of capital omega, then this will diverge, and this will become relevant soon. Okay, I told you that I wanted to tell you something about the analytic structure of this function, this implicit relation that I told you about. And in order to explain that, I need to talk a little bit about conformal field theory. Well, I guess most people here will know that in general, you can use conformal invariance to set up 2- and 3-point functions between primary operators, and also that you can, in general, give explicit formulas for 4-point functions if you know the 3-point functions, these structure constants, and you know the algebra, the underlying Virasoro algebra, by writing this function here, which is analytic, and it's called the conformal block. So this is completely determined by the dimensions of the external operators and the dimension of this inner operator and the conformal modulus T. So the T being in this case it will be exactly the position of the second one. Okay, there are many ways to compute this function here. It's a well-known function in conformal field theory. You can use some fast methods, recursions that have been proposed by Zamolodchikov in the 80s, and there's no really, I mean, there is some work being done in trying to understand this analytically, but there is no real issue how to compute them. The relation that I want to point out with what I told you before about this confluent Hawaiian equation comes from the so-called degenerate representation of the Virasoro algebra, which show up when the conformal dimensions have some discrete set of values. A particular one, which is this 2-1 family here, m equals 2, n equals 1, is particularly interesting because it satisfies the conformal word identity, which is written in this term. So this correlation function satisfies some second-order differential equation in the position of this field. And this field actually knows about monodromy because if you work out the OPE between this field and some other primary field, generically you're going to have a term that leading term that's non-analytic. So you see that as Z goes round W, this picks up some phase proportional to alpha. And this other term here, which is a different family corresponding to a different conformal dimension. And the descendant, the primary operator, and also the descendants. The descendants will have the property that they are analytic when Z equals W. So the non-analytic part is completely determined by the conformal dimensions of alpha and the B parameter of conformal field theory. Okay. So in order to relate what I wrote before, I'm going to take the semiclassical limit of this. So I'm going to take the limit of B equals 0, where this conformal dimensions also diverge, but they diverge in this scaling limit, and also the internal dimension diverge like this. It's a generic argument that hasn't been proved mathematically with mathematical rigor, but it's expected to be the case that this conformal block will exponentiate. So it will be written as the exponential of some semi-classical action of Liouville. It seems to be the case in this case. At least you can compute this and at least verify this order by order that it behaves like this. And that means that in this limit, the type of correlation function that I was considering here with this degenerate operator and these primary operators, it should factorize, because this degenerate operator is still light, where all these primary operators become heavy. So by physical grounds, you expect to have some background set by these heavy operators, and then some fluctuations around this given by the light operator. So this is a sort of wave function, and this would be the classical action which has this form. In this limit, the word identity turns from a partial differential equation involving all these derivatives with respect to the positions of these heavy operators to a ordinary differential equation that only involves the position of the light operator. And this is a Fuchsian type of differential equation. So it has the property that at every point it behaves polynomially. And this is expected from the generic facts of the OPE here. So the calculation of this W is also something like very established. They are especially coming with the AGT correspondence. You can write that in terms of Nekrasov functions in this Nekrasov-Shatashvili limit. It's quite cumbersome, but you can do that term by term. People Algebras, Marco Marinho, and these people at CISA, they have been doing that because there are also some nice relations to instant on partition functions in N equals 2. We can talk a little bit about that soon. Some continued fractions that we proposed a couple of years ago, which work very, very well, and also based on isomonodromy. And funny enough, this gives some expression for W, not in terms of semiclassical conformal blocks like the ones that I'm describing here, but in terms of C equals 1 conformal blocks when B equals I. Apparently there is some deep relation between this different representation of different Virasoro algebra, and this is better understood from the gauge, the N equals 2 Seiberg-Witten theory than from conformal field theory. But this is a topic for another talk. When you study that using this isomonodromy methods, which basically coming from this C equals 1 conformal blocks, the structure between this sorry about that. The structure between these functions, these prepotentials, like they used to call the semi-classical conformal blocks that I just defined here, this P magically turned into an S because I didn't check this enough. This actually parameterizes what happens to the solution, to this wave function as you go around the complex plane. So in this case here, the wave function has the properties that as z goes around each of this zk's, you have this polynomial behavior. But you may ask now what happens if you go around two of the primary operators. So say if you go around primary operator sitting at the origin, another one sitting at t. It turns out that the parameter sigma that I defined a few slides ago actually tells you how the analytic continuation is to be done around this point. And this function here actually determines how the analytic continuation works around any couple, or actually any number of singularities. In this case, there are just 4 of them. So some nice classical result that once you know this parameter eta, you can reconstruct all the monodromy parameters here. In our case, the situation is a little bit more complicated because, as I told you, the singularity at infinity is irregular, and you can work it out from the same theory. How does that work for irregular singularities? Because you can consider this irregular conformal blocks that are generated by not by primary operators but by Whittaker operators. Whittaker operators, they show up from collisions of primary operators in which you take this Liouville momentum to be equal and opposite, almost. You're going to take this parameter lambda to infinity at the end of the day, and you take out some part, lambda-dependent part that gives you a finite result at the end. The Wemmer modules associated to the analog of the Wemmer modules associated to the Whittaker operators, they are not annihilated by all positive L's, or L's with n positive, but they are eigenvalues of L1 and L2. They are annihilated by the rest of them. And the representation theory of the Whittaker works pretty much like the ones at the Wemmer modules. You construct the states by acting with L with negative index. And you construct this tower of states. I mean, in the end, it's the same. It's quite the same thing, but you're going to have this extra structure. If you plug this now in the radial equation, you have these expressions that give you this Liouville momentum of this Whittaker operator in terms of the frequency of the field and the mass of the field, and also this gamma parameter here, which is the eigenvalue of this L2. Also in terms of the 2, you see that this is actually, these are actually imaginary numbers. So this allows you to give an interpretation of what happens at this infinity point. It's not a primary operator that gives you the infinity point, it's a Whittaker operator. If you're going to ask me if this has any bearing about flat space holography, my answer will be right away, I don't know. As I told you, the rest of the game is basically set because you know that the in and outer horizons themselves are related to primary operators with this Liouville momentum. So, okay. With all this in mind, I mean, you have some way to compute that. The last ingredient that I have is that I told you that I want to solve the Sturm-Liouville type of problem. And as it turns out, the Sturm-Liouville type of problem can be cast in terms of these parameters. So, for instance, this for the angular equation, you want the parameter of this internal Liouville momentum to be just up to some even number, to be the sum of the Liouville momentums associated to the north and south pole. And the L here, or the even number, will have the interpretation of the angular eigenvalue. For the radial equation, the problem is a bit more involved. You need this eta parameter, and you need to show that the eta and the sigma parameter are related this way. This is usually different from the CFT 4-point function in the semiclassical case, in which you set this eta parameter by locating the saddle point of the semiclassical action. So I'm still trying to figure out exactly if there is any nice relation between. It would be nice to have a relation between the two of them, but this also means that the CFT interpretation in this case is just some mathematical tool. It is not something underlining or some physics. There is no obvious physics underlying it. Okay. Just to sum up, because I need to talk about the results, these parameters that I introduced, the monodromy parameters, sigma and eta, etc., they set the global aspects of solutions of the ODE. Many quantum mechanical problems are solved in this way because many quantum mechanical problems can be cast as a Sturm-Liouville type of problem involving Fuchsian differential equations or limits of Fuchsian differential equations. And this works for any Fuchsian differential equation. So it's a pretty old problem, yeah, but I can give you a solution to that. This solution can be computed efficiently in terms of CFTs, so this is a bit of a strange fact, but if I tell you, a mathematician, that the generalization of hypergeometric functions suddenly need this infinite dimensional algebra to be worked out, it will call me crazy, but again, this is what shows up. There's some effort in trying to make, at least for me, try to make some sense of the CFT, and I'm still not giving up, but there are some strange, not strange, but interesting relations. For instance, I guess I can tell you another one right away. You have sorry, I came out too soon. You have some problem of the angular equation to compute this angular eigenvalue. This angular eigenvalue translates to a problem which is given basically in terms of the derivative of this of the conformal block. So it basically means that in that case the lambda is given by this derivative of the conformal block in terms of some parameter associated to the north pole in the spheroidal harmonic equation. And then what you do with this, you fed this into the radial equation, and then you use that to compute the accessory parameter, the C, for the radial equation. So in the end of the day, you have some relation between the derivative of this prepotential associated to the angular equation being equal, in some sense, to the derivative of the prepotential associated to the radial equation. Now, if this were a CFT system, I would have two independent CFT systems that satisfy some equilibrium equation. So they had some thermodynamic equilibrium between them. This and the fact that this delta parameters here are associated to this entropy influx makes me think that perhaps there is some underlying physics, but as I told you, this is something that I need to work out. What I do know is that this method is efficient from the numerical point of view. I can put this in the computer and compute quasi-normal modes of black holes. So let me just gloss over the results. You can give expressions for the angular, spheroidal angular values. These are known in the literature. In this case, it's just a simple extension of the results known. Both for small parameter alpha here is related to the frequency of the mass like this, as well as for large parameters. The large part of the parameters just come from the fusion relations of CFT, so it's also something that you have control over. The radial equation is more interesting. Here I told you that there is some sort of equilibrium between these two, the CFT associated to the two systems. You can compute the things, but you have to do everything numerical because there are no natural small parameters. In general, A over M is some number between 0 and 1, and mu for any sort of realistic field is also less than 1, at least if you want to work in the linear regime. So they may be small, but they are not nice expansion parameters. Anyway, you can do this numerically. You have what is called in literature non-corrotating modes, and then you can plot whatever happens to the quasi-normal modes. You choose some quantum numbers, plot the quasi-normal modes for Schwarzschild case and for the extremal Kerr case here. You see, for instance, in this case here, where L equals 1 and M equals 0, so there is no coupling between the angular momentum of the field and the angular momentum of the black hole. There is some finite limit, so this has some finite decay time, even at the extremal value. By the way, this extremal value here is a limit that you can take smoothly. There is nothing blowing up there. Equations continue to be valid, even when A equals M over M equals 1. What is more interesting is that for L equals M, so the so-called co-rotating modes, you see that the real part goes to 1. This is a generic feature. Usually it goes to M over 2. And the imaginary part goes to 0 as the rotation parameter gets to extremal case. The frequencies, the quasi-normal modes frequencies near the points, they have a tower of values that whose imaginary part, whose decay times vanish as the temperature of the black hole. But as I told you, this is not the whole spectrum. These are called zero damp modes. So basically, what you have is some two categories of quasi-normal modes, two categories of perturbations. The ones that are zero damped at the extremal case, the imaginary part goes to 0, they live forever, and the ones that have finite part at the extremal point. As you increase the value of the mass of the field, something funny happens. You see that there is some structure near the extremal case. If you zoom in, you see there is some transitions. For small enough mass, the modes are zero damped, but if the mass is large enough, they become damped at the extremal case. If you zoom it there, and you locate that exactly at this point here of the mass, when mu is equal to 0.3705, which is surprisingly small. I didn't realize that until I plug in the numbers. It's something like 10 to the minus 11 giga-electron volts, but anyway, I found it nice too. You show that there is a bifurcation point, actually. So modes that, here I'm using some other coordinates in which the extremal case is to the left, and the modes, they come from this behavior where it falls down to 0.5, and this is m equals 1, small m equals 1. When you go to the extremal point, it goes to a finite point. Here is 0.008. And this is just numerics. We're trying to find some inkling of what's going on here, but this happens at some exact point in phase space. So when the angular momentum is 0.999466, so between 466 and 4655, this happens. So there is a transition between this zero damp mode to the damp mode if the mass increases above that value. And the bifurcation point is some particular point in phase space. If you plot the first overtone, so n equals 1 and n equals 0, something funny happens because n equals 1 continues to be a zero damp mode, so at some point the imaginary part of the longest lived mode ceases to be the longest lived mode, and becomes faster, decays faster than n equals 1. Actually, this happens for larger points as well. I'm trying to understand that a bit better. For this particular point, the two modes actually are very close together. If you analyze what's going on near the point, this is the particular point where they become very close, they change place. The n equals 1 mode goes from damped to 0 damped, and n equals 0 mode goes from 0 damped to damped. So there is a point here in which there is some exceptional degeneracy. At this particular point, these two modes, they should have the same frequency, which is sort of odd because you have these non-crossing theorems, but the effective Hamiltonian here is no emission, so this may happen. This actually does happen, show that. This gives the, there's another way to see this here. In this case, you see this from the first overtone, that these are the graphs that people working in linear perturbation numerically, they are more used to the parametric graph between the real part and the imaginary part. But you see, for instance, the real part here passes through some part where it decays to 0 as you go to the extremal point, where you have some oscillations. And the behavior at the extremal point is non-zero. There's some non-trivial real and non-trivial imaginary part. Here you have this bifurcation point between the fundamental and the first overtone, and here the bifurcation point between the first overtone and the second overtone. The bifurcation point is the endpoint of some curve in which the imaginary part of the first overtone is equal to the imaginary part of the fundamental mode. So this is a sort of point, over this line, the two of them decay at the same time. So in general, if you place the black hole here, the black hole will decay in a superposition of these two modes. Well, the real part is different though, so that means that there's some discontinuity there. This actually has some very nice similarities to the theory of phase transitions. If you remember the theory of phase transitions between, say, liquid water and vapor, you have some coexistence curve, and the coexistence curve stops at the critical point. And what's happening here is, in this dashed line here, seems to be something like that. Here you have some eigenvalue, and you are ordering the eigenvalues by their imaginary part. And over this line, the two eigenvalues are, the imaginary part of the two eigenvalues are real, but they change places. What is the lowest eigenvalue here becomes the second lowest eigenvalue here, and vice versa. And this ends at this point where both of them have the same eigenvalue. So how do you translate that to the theory, or to thermodynamics? Usually you work in the thermodynamics phase space, and in water, for instance, this would be the pressure and the volume. Here you have liquid water, so if you somehow were able to compute the transfer matrix of the system, you'd find that the largest eigenvalue that nominates the thermodynamic limit would be associated to the liquid phase. And here, the largest eigenvalue would be associated to vapor. The coexistence line, both of them are equal, but there is some discontinuity in the derivative. There's some discontinuity in the free energy here. You can go round one phase to the other, going past the critical point where both of them are equal and there is no discontinuity, and then you can move between one eigenvalue or the other adiabatically if you go around here. So if you carry this analogy further, you can ask yourself what happens if you go adiabatically past this coexistence line between a region here to the left of it to the region right of it. And what happens is exactly what you expect. The first overtone and the fundamental mode, they change places. What was the fundamental mode here becomes the first overtone if you go through one direction, and remains the fundamental mode if it goes to the other direction. So they change places, and then you have some hysteresis here, which is exactly the kind of thing that you've seen in ferromagnetics. If you remember that you have some chunk of metal, of ferromagnetic metal, with no magnetization, but if you apply a magnetic field, it polarizes. Even if you remove the magnetic field, there is a system there. So the system has some memory. And this is what happened here. If you find the system oscillating at some particular value here, it means that you have brought the system from this other place at some other state. So it remembers not only the state where it is at a particular point, but also how you get there, at least if you work adiabatically here, like here. This bifurcation point is actually the branch point of a two-sheeted surface of frequencies. So try to visualize here that if you go, you begin from this point and then you go around this line here, you end up at this level, and then you can continue past and you go to this, you jump over back to this sheet in this, but now you're following this white surface, and then you end up in this level here. If you go this around this two-sheeted surface twice, you end up at the same point. So there's a sort of square root branching point here. I'll try to phrase that a bit better. But this means that there is a geometrical phase here. So usually, it would be called Berry phase if this was a emission Hamiltonian. Okay, so I guess I talked what I had to. There is some analog in which you can understand this. Black hole perturbation theory, although it has nothing of the sort, it has the same kind of structure that you find in more complex systems like statistical systems. There is a line of coexistence of phases, in this case two of the overtones. They end up at a critical point, and you can have this hysteresis around this if you go around it in different paths. Well, you can make the joke, I guess, that this would be, if this was a condensed matter system, this would be a good candidate for a quantum knot gate, because in a quantum knot gate, usually you feed the system with some particular superposition of two eigenstates, and then you move it adiabatically in parameter space until they are interchanged. And this is exactly what's going on here. If you go around the exceptional point, the first one, the first overtone and the fundamental mode, they change places. Of course, this is not I cannot write a grant to get money from people in quantum information system, but I guess that's something that's a contact with the topic of the workshop. The good thing is that it's a bit impractical. You need the solar-sized black hole very close to extremality, but at least it's a long-lived one, and I can have this for a couple of hours because of the low decay times. The point that I guess that well, there's a mathematical point that what allowed me to solve the system beyond what's known from this numerical studies that people at technical are experts on, is that I can solve the system and have some analytic control of the solution. And this means that I better look at this conformal blocks, at least the semiclassical conformal blocks, as a new class of special functions that I probably should learn more about the analytic structure, not only because I want to understand conformal field theory, but because I want to understand the solutions to this type of quantum mechanical problems. The other thing that I would like to pass the message here is that the existence of hysteresis, geometrical phases, accidental degeneracies is generic for this no-emission system. So particularly any system that you can actually write down using separation of variables, or any wave equation in any background that you can write down using separation of variables to a system of ordinary differential equation, if they have rotation, they should display the same features. So particularly black holes in ADS space, they should also have this same features. It's just that they may not be in a physically accessible point in parameter space, but the simple fact that they may exist is actually, I think it's actually something that has relevance to ADS-CFT. So, okay, so I guess that this is it. I'd like to thank you all for listening.
So we have a few minutes for questions.
At some point, you mentioned that you have a continued fraction technique for computing a conformal block or the derivative of W. This is a continued fraction of which numbers?
I'm not sure I understand.
This continued fraction technique, how exactly does it work?
Well, it's more of a numerical method, but you can use that for analytic expansions. I don't know if that answers your question, but let me just write down the, yeah. So basically these coefficients, capital A, B, and C, and D are coefficients that you can construct from the equation. And then you propose some expansion for the accessory parameter. For instance, in my case, is the derivative of the conformal block. And I find some implicit relation between the derivative of the conformal block and this parameter sigma that has to do with this intermediate channel. And then I can solve that recursively. This is explained in this JHAP paper from last year. I can give you the reference. The good thing, I mean, the novel thing is that, and it's not particularly relevant for the philosophy, but it is a very efficient way to compute irregular conformal blocks at the infinite momentum limit, at the infinite conformal modulus limit. And I was under the impression, at least at the time where I put the paper out in the archive, that was a new result. Nobody knew how to do that before.
Yeah, good question. So again, you described the differential equation that you get for the null state decoupling from a conformal block, and then you immediately jumped to the sort of the equations, the Dukowski equation, at least the equations for normal, quasi-normal modes.
Yeah.
And indeed, at the level of differential equations, you can see that they kind of look identical. But that's just a phenomenological observation.
Yeah, exactly.
There's not, or do you have any guesses of why these things look
no, there are hints. There are hints that there is something. Perhaps it's the Liouville sector of the underlying theory.
Or that the conformal block means something in terms of a mode. And
there is something that's very appealing, at least to me, is that this relation between the Liouville momentum and the entropy intake is pretty generic. It happens to lots of different black holes, ADS black holes. Vector ADS black holes is a different beast. It's more complicated, but people know still too little about how to separate variables there. But 4-dimensional black holes and 5-dimensional, well, 3-dimensional black holes, there is no, I mean, it's a known problem. 4-dimensional black holes and 5-dimensional black holes, they seem to go over this pattern. So what's the problem? The problem is that if I want to find a way to find what B is, right? I want to conflate B with H bar, or square root of H bar. And there's no way to do that. It's semi-classical. So one thing that we would like to know is, okay, now if I introduce corrections, H-bar corrections to H, do they follow the same pattern? I don't know that. Perhaps it's...
Yeah, but even at the leading order, I would say it's already...
But the real problem, at least for this to work, is that semi-classical conformal blocks have a definite value of sigma, because that's the point where you have the saddle point of the form. And it's not the same saddle point that I have here. Okay. Perhaps there is a way to analytically continue that, but I need to look further. If you find a way to figure that out, I guess you have a good case, right? I mean, it seems more convincing that way.
At the moment, it seems like a suggestive.
No, it's just, I'm not claiming that this is anything more than a mathematical tool. But even if you just treat it as a mathematical tool, there are some things to be gained. Now you're able to continue to at least adiabatically follow the modes between Schwarzschild and the extremal case. This was not done before. So, for instance, you could not locate these extremal points before because there is no way to analytically continue those modes to Schwarzschild to see what's going on.
More questions? Okay, so let's thank Bruno again and come back at 4:15.